Hello Algebra 2. This video lesson is about exponential growth. We covered the material of Chapter 8.1, and with Chapter 8 we begin moving the variable, the unknown, into the exponent's place. So here, for example, I've given you the equation y equals 3 to the x power. In order to graph this, well, just like I just did with you for Chapter 7.5, where we were talking about graphing root functions, I recommend starting by making a table of x, y values. So for example, let's say I put 0 in for x. Well, 3 to the 0 power, or for that matter anything to the 0 power, is 1. If it's 3 to the first power, well, that's 3. 3 to the second power, of course, is 9, and so on. And I graph those points like so, or plot those points, but notice that I really can't go beyond where x is 2 here on the graph paper that I have, because when x is 3, y is way up screen, up high here at 27. So I draw a curve through what I do have available. But what would happen if I'd looked at negative x values over here? Well, if x had been -1, 3 to the -1 power, remember that just means that the 3 is on the wrong side of the dividing line, and so it should be 1/3. 3 to the -2 power, it's a little hard to read with my handwriting here, but that ought to be 1/9. It's 1 over 3 to the 2. So I plot those similarly, and you see that I start, as I go to the left from this place, I go lower and lower. And here's how the textbook represents it. In their case, they're looking at 2 to the x power, where I've been looking at 3 to the x power, and they do plot 3 points to the left, these 3, where I'd only been able, with my handwriting, to fit 2. But notice, similarly, they get this diminishing amount for the y value as you move to the left, and rapidly growing y value as you move to the right. That's the classic pattern of exponential growth. You go from very little happening to the amount shooting almost through the roof. Now, here are a number, don't worry about the matching instructions here at this point, but here are 6 different graphs and 6 different exponential equations, exponential functions. Notice some of them are shooting upward and some of them downward. At this point, that's all I'd wanted you to see. And to point out that the ones that are shooting downward are simply doing so because they've got negative coefficients on them. So let's not worry about the matching, but what I do want you to notice is that in every case, well, let's call it a runway, that's what I tend to think of it as, the runway is off to the left, whether it's shooting upward from that runway or shooting downward from that runway. You're not seeing any, and I've simply flipped this graph here, you're not seeing any cases where the runway is off to the right. We will talk about those, but not in Chapter 8.1. That's a different situation than what we have here. That's not, this red curve here does not represent exponential growth. So the textbook, walks you through in example 1 how to graph this function here, 1/2 times 3 to the x power, only by plotting 2 values. I was surprised by that, but it puts in 0 and 1 for x, and 3 to the 0 power, of course, is 1. 1 times 1/2 is 1/2. 3 to the second power is, 3 to the first power is 3, and 1/2 of 3 is 1/2, or 3/2. So they have drawn the curve with just those 2 points. I really think in order to draw a curve at bare minimum you really need 3, but I'm just walking you through, if you've already read it, what the textbook is showing you in example 1. And then they give an example 1b. The only change here, and now we start talking about what happens when you have a negative coefficient. Instead of 1/2 times this, you've got 3/2 to the x power, but it's times a negative. So again, plug in 0 for x. 3/2 to the 0 power is still 1, so that's -1. And 3/2 to the first power is 3/2, so the y value is going to be -3/2. And again, like before, they've plotted those 2 points and they've drawn a curve through it. Again, I would much rather see a third point here. They really ought to have put in 2, I think, as a third value for x, and checked to see what y is to draw the curve more accurately. But let's move on to the more important part of the lesson, which is our old friends h and k. You can adjust the value of the exponent beyond the fact that there's a variable here, an unknown x. You might add or subtract something to or from that exponent, and you also could add or subtract a value outside of the exponent. Well, anything that you add or subtract, anything that you do to modify the exponent is going to move the graph horizontally. And anything you add or subtract outside of this term is going to move it vertically, just like it has before. So, as an example, if I'd had as my original 1/2, let's just cover up 8 and 9, and let's just look at 7. No, I guess we have to, unfortunately, the way I have it set up. In this case, G is going to be 1 space to the right and 2 spaces up from whatever generic graph I would have drawn for this. Similarly, if this is my generic graph, then this is going to make it move 2 spaces to the left. There's no up or down because there's no k value, but it is going to be, because it's a negative, it's now going to go downward, and remember the runway therefore is going to go that way instead of the runway with the original generic going upward. For 9 here, I'm moving 2 spaces to the left and 4 spaces downward, every one of those points. So here's an example or an illustration of that happening. The dotted line is the generic graph for this. Let me circle it here for you. For this here, 3 times 2 to the x, or as they say it here, that's this graph here, this dotted one. Now, adding in the influences of h and k, the -1 means that I move 1 space to the right, and the -4 means I move 4 spaces downward. So that's what they've done here. Every one of these points, they moved 1 space to the right and 4 spaces down. And same thing here, 1 space to the right and 4 spaces down. That's how they've moved that graph based on h and k's influence. Also notice that they asked for the domain and range. They're talking here about the finished graph, the solid curve, not the dashed curve. For the solid curve, left to right, I can have any value I want, any x value. There's no reason why I couldn't put any x value in here. I could put in 0, I could put in a square root, I could put in pi, anything I want to can go in for x. But my y results, well, this runway that I've talked about here becomes a limit. You're really never going to go below -4. So the range is that y has to be above -4. Now, as I've said before, these tend to shoot through the roof or through the floor, depending on whether the coefficient's positive or negative, but there's not going to be any ceiling on this one. There is a floor, though. This runway off on the left side of -4 is creating a floor, and y is always going to be greater than that value. And that runway is called an asymptote. It happens, well, let's look at why it happens. Let's look at this table of x and f of x, or y values. Notice if you work backwards here, instead of looking at the larger x values, look at what happens when the x value becomes negative. -1, you get a half. -2, your result is a fourth. -3 becomes an eighth. It keeps becoming a smaller and smaller fraction. But it's always going to be a fraction. Whether this is -3 or -300, it's still going to be a fairly small fraction. Slightly larger than 0. And that's one of the characteristics of an asymptote. An asymptote is a line, as it says here, that almost touches, approaches, but the line approaches, but never quite touches as you move away from the origin. So as you're moving to the left here, it's approaching in this case 0, but never quite touching 0. And notice I say in this case 0. Look at what would have happened if the function had been 2 to the x power plus 2. Well, in that case, just looking at these negative x values here, instead of 1/8, I would have gotten 2 1/8. Instead of 1/4, 2 1/4. Instead of 1/2, 2 1/2. It's always the influence of this first term here, the 2 to the x, becomes smaller and smaller as it approaches 0. But that plus 2 is always going to be there. So the asymptote in this case is going to keep approaching 2. And that's one of the things about an asymptote. An asymptote's value is always, in these functions that we're going to talk about, be approaching the k value that's dangling off to the right in the function. So these as examples here. The asymptote for this equation is going to be at 2. The asymptote for this one is going to be at 0 because there is no k value over here. The asymptote, lastly, for this one is going to be at -2. That runway is going to be where y is -2. Based on me having said all of that, look at these 9 examples. Figure out what the asymptote is for each of the 9. Hit the pause button. When you come back, I'm going to tell you whether or not you're right. Okay, I'm going to assume that you've paused, you've thought through all 9 of these, and you're ready to hear the answers. There's no k showing here. The asymptote's at 0. Same thing for 14. For 15, the k value is 1, and that's what the asymptote will be. For 16, it's -3, 17, +2, 18, -3, 19, -4, I think you see the pattern here for sure, 20, +1, and lastly, for 21, it's at -1. Last thing I want you to do, and in the interest of time, I'm not going to actually show you these graphs. I will post the graphs instead on my website, and you can come back and check them, but they're not going to be part of the video. But I want you to go ahead and graph 14, 15, and 19. Again, the way to do it is to start by making a table of values, like with chapter 7.5, like when we were graphing root functions. I recommend that you start with the generic. In this case, the generic is going to be 2 to the x power. And similarly here with 19, the generic is going to be 2 to the x power. And then make that graph and then shift that graph based on the influences of h and k. Come back to my website when you're done with that and compare those to the answers that I'm going to post there. That's it for the video lesson. I look forward to seeing you in class. Bring any questions that you have.